So objective of the class is to learn about pH scale. Earlier also you have learned this in your previous classes. So once again we are going to learn about the pH, its importance, its application. We have to understand what is common ion effect, and we are going to learn its application also. So that is the objective of the class. So let us look at the concept and definition. pH scale was introduced by the Danish biochemist S.P. Sorensen in 1909. So how it is defined? It is defined as the negative logarithm, negative logarithm to the base 10 of the concentration in moles per liter that of hydrogen ions which it contains. So pH is equal to minus log H plus. For pure water or neutral solution, hydrogen ion concentration comes to be 1 into 10 raised to minus 7 mole per dm cube. So pH is equal to, when you put the value of hydrogen ion concentration, the value comes to be 7 at 25 degrees centigrade. This 0 should be at the top. So it is not 250, it is 25 degrees centigrade. So once you look at this pH scale, it starts from 0 and ends with 14. Okay. So 0 to 7 is the acidic part, 7 is neutral of course, and above 7 is the alkaline range or the basic range. So you can see here battery acid 0, sulfuric acid 1, the gastric which is present, okay, HCl in the stomach, that is also having the pH 1. Then lemon juice is 2, orange juice is 3, banana 5 to 5.3, okay, acid rain 4.2 to 4.4, that is a acid rain when we get because of the air pollution, the pH scale is 4.2 to 4.4. Milk is 6.5 to 6.8, pure water it is 7, eggs it is 8, baking soda is 9, milk of magnesia which is given as antacid, right? It is having the pH 10 alkaline, ammonia 11, soapy water it is 12, bleach is 13, liquid drain cleaner, okay, that is having 14. So this is about the pH scale. It is defined as the negative logarithm to the base 10 of the molar hydrogen ion concentration. Okay. So pH is a scale to measure the acidity or alkalinity of a solution. Scale ranges from 0 to 14, 7 being neutral, less than 7 indicates the acidity, greater than 7 indicates the base. It is a measure of the relative amount of free H plus and OH minus ions in the water. It is a measure of the relative amount of free H plus and OH minus in the water. It is a logarithmic and inversely indicates the concentration of H plus ion in the solution. It is logarithmic and inversely indicates the concentration of H plus ion in the solution. So measurement of pH is important in the chemistry, medicine, water treatment and many other applications. Okay. So buffer solutions. For some reactions, maintaining appropriate pH is important in order to carry out the reaction. So in that case, pH of the solution becomes very important. Similarly in medicine, you know all the reactions which are taking place in the body, they occur at definite pH. If there is slight change in the pH, the reactions may not take place. Then in water treatment, the water which is discharged from industrial effluents, they have to be of appropriate pH before discharging into the water bodies, okay, and many other applications. The next thing is we are going to learn about the common ion effect. So it is an effect that suppresses the ionization of an electrolyte when another electrolyte which contains an ion which is also present in the first electrolyte, which means which is common to both. Once again I'll repeat, it is an effect that suppresses the ionization of an electrolyte. Usually it will be weak electrolyte, okay, by adding another electrolyte which also contains the same ion which is present in the earlier electrolyte. So that's why we call it as common to both. That's why common ion effect. So definition, it is a separation of degree of dissociation of a weak electrolyte. It is a separation of the degree of dissociation of a weak electrolyte by adding a strong electrolyte having a common ion. By adding a strong electrolyte having a common ion is called as common ion effect. So NH4Cl is a strong electrolyte. It is going to dissociate completely into NH4 plus and Cl minus, and NH4OH is a weak electrolyte. It dissociates into NH4 plus and OH minus. Weak electrolyte ionizes partially. So NH4OH, it ionizes partially, attains equilibrium, NH4 plus and OH minus. Strong electrolyte ionizes completely. So if you look at these two examples, now which are the common ions here? NH4 plus is a common ion. Okay. So this is the common ion effect which is going to suppress the degree of dissociation of weak electrolyte. So which is weak electrolyte here? NH4OH is a weak electrolyte. By adding strong electrolyte, that is NH4OH, which has NH4 plus as common ions. So this common ion effect is very nicely explained with this picture. The process in which ionization of a weak electrolyte decreases or suppresses by adding a common ion from outside is called as common ion effect. So this is a weak electrolyte. Earlier we have seen NH4OH giving rise to NH4 plus and OH minus, for example. Strong electrolyte is NH4Cl giving rise to NH4 plus and Cl minus. So if you look at the color, these NH4 ions are the common ions here. This is the common ions. And these common ions are going to prevent the dissociation of a weak electrolyte. Okay. So this is a beautiful picture. It is self-explanatory. That's why I thought of putting it here. Now just let us discuss common ion effect once again. So weak electrolyte ionizes partially, attains equilibrium. So this is a weak electrolyte. Partially it is going to ionize and attain the equilibrium, giving rise to NH4 plus and OH minus ions. Applying law of mass action we get, so Kb, dissociation constant, is equal to concentration of NH4 plus ions, that is the product side, plus into concentration of OH minus ion divided by concentration of undissociated NH4H. So Kb, dissociation constant value fixed for given electrolyte and given temperature. NH4Cl ionizes completely as NH4 plus common ions. So this is strong electrolyte, completely it is going to ionize, giving rise to NH4 plus, which are the common ions to both. Concentration of NH4 plus increases. Now since NH4OH is partially ionizing, NH4Cl is a strong electrolyte, it completely dissociates or ionizes to NH4 plus. Naturally, concentration of NH4 plus ion is going to increase. So that's why what happens is Kb will be disturbed. Equilibrium constant, it will be disturbed. So in order to keep Kb constant, concentration of OH minus ion should decrease. So if you look at this Kb, since NH4 plus is increasing, concentration of OH minus ions should decrease, isn't it? It should decrease. And concentration of NH4 OH ions should increase. So this is on the denominator side. This is increasing. This has to decrease. And NH4 OH ions which are at the denominator side, it should increase. So sum of the OH minus ions combine with NH4 plus. When concentration of NH4OH will increase, when some of the NH4 plus ions, they are going to combine with OH minus ion to form undissociated NH4OH. Okay. OH minus should decrease and concentration of NH4OH should increase. So what happens is OH minus ions combine with NH4 plus, forming feebly dissociating NH4OH. So shifting the equilibrium to the left. Now what is happening over here? NH4 concentration is increasing. So reaction takes place in the forward direction. So in order to stop that, in order to increase the concentration of NH4OH, these NH4 ions, they have to combine with OH minus ion and give rise to NH4OH. So reaction has to be shifted towards the back. Okay. So same thing is happening over here. Shifting equilibrium to the left, thus degree of dissociation of NH4OH is suppressed. So if you shift the reaction towards the left hand side, that is undissociated NH4OH concentration will increase, and which makes the Kb constant, okay, or stable. So common ion effect can be achieved also by adding a strong electrolyte like NaOH, KOH having OH minus ions, common ions. So here we have taken example of NH4OH as a strong electrolyte. Instead of NH4Cl, we can also add here NaOH and KOH, which are the strong bases which have got OH minus common ions. Okay, which have OH minus common ions. So that effect can be also achieved. Instead of adding NH4Cl, we can add NaOH and KOH to have the same effect. Now let us look at the application part of common ion effect. So first application here is in the qualitative analysis. So in PUC second year or first year, we have learned the semi-micro qualitative analysis. So what we do there, particular group radicals are separated from the mixture. Okay, at a given time, only one radical can be precipitated out of the solution. What is precipitating out of the solution? Its solubility decreases. That's why a particular compound or the PPT, it is going to separate out of the solution and settles at the bottom, isn't it? So application part over here is when we add group reagents, for example H2S, etc., isn't it? So once we add the group reagents, what these group reagents they do, they are going to react with the radical of the particular group and forms the PPT, isn't it? It forms the PPT, and that is used in order to spot the radical of a particular group. So that's why the qualitative analysis, it is useful. Similarly, salting out and salting in. So what is salting out? Decrease in the solubility. Decrease in the solubility. When the solubility decreases, what happens? Naturally, the compound is going to precipitate out. So increase in the salt concentration leading to decrease in the solubility and then precipitation is called as salting out. What is salting in? Mild increase in the salt concentration, increase in the solubility. Mild increase in the salt concentration, increase in the solubility. That is the salting in. So let us see the further application part. So these are the other applications of common ion effect. As I said, it is used in the qualitative analysis, that is the group separation of the radicals. Then purification of the salt. Purification of the salt, it is useful. So what is purification of the salt? When we take the brine, when we take brine solution which is in the impure form, so what happens is, once you bubble HCl gas, once you bubble HCl gas to that particular solution, now this HCl and NaCl, which are the common ions there, Cl minus ions Cl minus ions are the common ions. So these Cl minus ions, once it is HCl gas is bubbled through the solution, it is going to decrease the solubility of NaCl. So once it decreases the solubility of NaCl, this NaCl is going to settle. NaCl is going to settle at the bottom. Saturated, once again I'll repeat, saturated solution of impure NaCl When it is transferred to container and HCl gas is bubbled with the help of pipe, as a result, pure NaCl will get precipitated from the impure solution, leaving behind the impurities in the solution. So that is the application of common ion effect in the purification of salt. Similarly, the common ion effect can be used for the salting out of soap. Now soap, what are soaps? Soaps are nothing but the sodium or potassium salts of long chain fatty acids, isn't it? Sodium stearate, palmitate, etc. So KOH and NaOH solution on oils and fats, they form the triesters of glycerol. KOH and NaOH, when it reacts with fats and oils, which are the triesters of glycerol, and with the higher fatty acid, as a result of this saponification reaction, okay, glycerol plus soap are produced. So what are these soaps? Soaps are nothing but the sodium or potassium salts of long chain fatty acids. So to separate the glycerol from soaps, soaps are precipitated by adding calculated amount of sodium chloride to saturate the solution. Okay, so that is because of the common ion effect only again. So sodium ions will be the common ions in that case. So equilibrium is shifted to left and the soaps get precipitated out of the solution by the addition of the salt NaCl. Okay, so that is about the application of the common ion effect. So let us revise once again what we learned about the pH scale. So pH scale is very important. It starts with 0 and 14. It is negative logarithm to the base 10 of molar hydrogen ion concentration. It is important in medicine, in chemistry, in the industrial application, isn't it? So that is the importance of pH scale. Then common ion effect is, it is a decrease in the solubility of weak electrolyte by adding strong electrolyte having a common ion effect. So that is the common ion effect. Application is in the purification of soaps, salts, isn't it? In the salting out of proteins from the solution, that is one of the application, as well as the semi-micro qualitative analysis. So this is about the application of common ion effect. So thank you very much for the attending class. Next time